do not perform these demos without proper safety precautions. We have years of experience plus safety precautions keeping us safe.
Alright, so this first demonstration that we've got is the whoosh bottle. So named because we're going to put some alcohol in here, we're going to burn it, and as it comes out the opening of our 5-gallon water jug, it's going to make this like whoosh sound. So the reaction that we are going to do is we're going to use a little bit of ethanol. You can also use a combination of ethanol and isopropanol, or you can just use isopropanol. All of it works. Just works to like varying degrees of speed. The ethanol will burn a lot faster than the isopropanol will. So if you want like a slow, gradual burn, use the rubbing alcohol. If you want quick, use the ethanol. Now, I don't want ethanol liquid because ethanol liquid just does kind of this boring little flame. I'll show you real quick if you've never seen an ethanol flame before. It's blue, which is kind of cool, but it's not really that interesting. Ethanol flame, just kind of blah. So what we are going to do is instead of using the liquid ethanol, we want to vaporize the ethanol that's in here because ethanol vapor burns much more interestingly. Now I'm just going to dump out the rest of the liquid ethanol. If there was liquid ethanol left in here, then it would just burn, and seeing as this water jug is made out of plastic, that wouldn't do so well. Alright, so just going to light a match, drop the flame in, or drop the fire in. We're going to get the light so y'all can see a nice pretty show. And here we go. Woo! There you go. That is the whoosh bottle. So for this next demonstration, we are going to do what's called elephant toothpaste. No, we are not actually going to make toothpaste. We are going to make a hydrogen peroxide decomposition. We're going to catalyze it with some potassium iodide. And the reason that it's called elephant toothpaste is that once we do that, we're going to capture the oxygen bubbles with soapy water. And all those oxygen bubbles are going to take that soap and kind of, you know, have it come out the top of this thing, and it's going to look like you took a giant tube of toothpaste and just squeezed it. So first we got to get set up, make our little soapy water, and get our catalyst in there. So that's what I'm going to do first. And then just to make it a little more interesting, Aquafresh is my favorite toothpaste. So I'm going to doctor this up, make it look like Aquafresh. Alright, here we go. Just adding in some 30% hydrogen peroxide. Not the 3% that you get at the grocery store, that wouldn't be potent enough. And this is one time when I wish that you could actually kind of like, I don't know if you can see the steam coming off, but this reaction is actually very exothermic. This one is called the sugar snake, and all I have in here is a little beaker full of just plain old table sugar, and I'm going to add just a little bit of water to it just to kind of wet it down. Not a whole lot, not even enough to like make it a true solution, but just enough so that all of the sugar has been coated down with water. Give it a little stir just to make sure I got it all in there. You almost want to make like a sugar paste. Okay, so So what I'm going to add to this is the dehydration of sucrose. Sucrose C12H22O11, we're going to use concentrated sulfuric acid to remove the waters from the sugar, leaving behind only carbon. Give it just a second. You can see that basically what's happening is the sugar's, it's starting to cook. You can kind of think of it, cook with the acid. And then as it cooks, slowly that water starts to come out. And now you see why we call it the sugar snake. Kind of looks like a snake coming up, although sometimes I just think it looks like a really big turd. And again, the vapor coming off of that is the same water vapor that we had before. And what we have left over here, our little sugar snake thing, is just pure carbon. And again, this is a very exothermic reaction, but this is cooled off enough. This, if I can pull it out, this is a solid hunk of carbon. It's very spongy because of the water vapor, and very lightweight because it's carbon, and that's how carbon is. But it's pretty cool. It's like a hard sponge. So there you have it. Okay, so decomposition of potassium chlorate, and we are going to do this one by taking the potassium chlorate and heating it on a Bunsen burner until it melts. And what's going to happen is that potassium chlorate, as it melts, is going to release all those oxygens, leaving behind just the liquid potassium chloride. And then we're going to take that superheated oxygen, we're going to introduce a piece of candy. In this case, we're going to use a Skittle. This can be done using any, very concentrated sugar source. Usually it's done using a gummy bear. We call it the Screaming Gummy Bear. But we didn't have any gummy bears. We have Skittles and candy canes. So we're using Skittles because they work better. So I'm just going to heat this to the point that it melts. So once all of the potassium chlorate has melted, you'll actually be able to start seeing the test tube fill up with oxygen. And once the test tube has filled all the way to the top with the oxygen, it's about halfway there right now, then I'm going to drop the candy in. Alright, so our test tube is filled with oxygen, and here we go with the candy. And what happens on this reaction is you have the heated oxygen and you introduce the sugar, and so you basically have a spontaneous combustion with the sugar and the oxygen to produce carbon dioxide, water vapor, and then all this black gunk in the bottom is basically the other ingredients in the candy just having been burnt to heck and back. You are going to see the synthesis of magnesium oxide from some pure magnesium and the oxygen in the atmosphere. Now, yes, we have secondary reactions going on. Magnesium reacting with nitrogen to produce magnesium nitride and a few others, but it's just a really fun reaction because magnesium glows really stinking brightly. So just introducing a little heat to get the magnesium going. And then once it's going, of course you don't want to look right at it. You want to try to kind of look off to the side. But once you've said that, you just can't help but look right at it, and then you're seeing stars for a little while, which is why I call this one the magnesium star. That's a big piece of magnesium. Alright, and then what we have left over is the very fragile, brittle solid of magnesium oxide. So for this one, we have a couple pieces of zinc, and I'm going to pour some hydrochloric acid over it. This one is called exploding egg. Obviously zinc and hydrochloric acid don't really have a lot to do with an exploding egg, but the hydrogen gas that's produced and this little egg right here that we're going to put over the top of this reaction, and let that blown out egg fill up with hydrogen gas. And those of you who have actually taken chemistry, you know that hydrogen gas is quite combustible, flammable, whatever you want to call it. Woo! Last reaction that we're going to do is the methane mamba, and it's called this because we're going to bubble some methane through soapy water, and that soapy water is going to trap the methane bubbles, and as this tower builds, you'll actually see that it has this kind of like wave to it, like a snake or like the mamba, the dance, and then we're just going to light it on fire and have ourselves a nice little combustion. And a really big fireball. This is always a fun one to do. Woo! Gotta love it. Another little one. So that was this year's day demos. Hope you guys enjoy the show, and I look forward to seeing you guys next year. Door.
Industrial strength.
Whoa! Oh my God!
That's awesome!
What's going on?
Still going too.
That's cute.
Does look like toothpaste.
Now, the two products of this reaction, we're going to just go. And there's still a little bit left in there.
Still on.
You're angry.
It's like those birthday candles that don't.
Come on!